Hi students! I know you're here today with the sub, so I want to tell you just a little bit more in your notes, finish your little sections, and set you up for the walk around, which you're going to do for the sub today. And then I'm going to see all your work, maybe even a quiz tomorrow on the walk around. So listen carefully, get through the day, be nice to the sub today, and I'll see you on Friday. Okay, let's talk about heterogeneous mixtures. We're actually on page 2, I think, of your notes. So go to the first page and turn it over. This is a little section that I skipped. It's not very long, but I want to tell you a little bit more about cooking and soaps and how to do wash. But we're going to start with something called a suspension. It's not a solution. It's a mixture containing particles that remain while thoroughly mixed, but then they settle out. Can you think of an example? Well, don't think too hard. You may have even read this in the last section of your book. But how about muddy water? You write that down. See where the little book is in your notes? Write down muddy water. But think about it. Muddy water is not a solution. The particles in the mud are so large that they actually settle out with gravity. So notice the tank on the right. Notice how over time these large particles settle, and so therefore they aren't dissolved. It's not like a solute dissolving in the solvent. Here's another example, kind of showing you on a molecular scale. There's chalk, which is a solute, water, which is a solvent. But yet again, you're not breaking the intermolecular forces, and the molecules can't actually intermingle. They're too large. So again, we call it a suspension. Large particles that settle out with gravity are called a suspension. Here's another example, a colloid. Again, not a solution. A colloid or colloidal dispersions are suspended particles that are larger than a molecule, so they're too big to be a solute, but they also don't settle out with gravity. They just kind of hang around. They give you a particle size there, 10 to 2,000 angstroms. So can you kind of think of a solution that never settles out and doesn't dissolve? Here's a bunch of examples. Smoke, whipped cream, milk, paint, marshmallows, butter. Kind of some crazy examples. There are some more in your notes too. So here's fog. Fog is a colloidal suspension. It's kind of like water just hanging around in the atmosphere. It doesn't settle out with gravity, but yet it's actually not dissolved in the nitrogen gas in the atmosphere. How about shaving cream? It doesn't settle out. Now over time it may dry out and then it goes away, but it kind of hangs around as a suspension. Now this last one, that was my dog. The last one is I want to show you in class. It's a specific example of colloidal particles that scatter light. It's called the Tyndall effect. So I will set up a demo in class on Friday and show it to you. But you've seen this before. A very simple example of the Tyndall effect would be a searchlight. You know, when a new movie opens or you're going to, I don't know, a play or the opera, and they have those big searchlights, and then in the fog, they kind of reflect light. And they scatter it. And so that scattering of light is called the Tyndall effect. Here we have hydrophilic and hydrophobic colloids. Now we talked about this just the other day, right, in the lab. I guess that would be yesterday. Looking at hydrophobic molecules that don't like water versus sodium hydroxide that we did the little molarity example with, which was hydrophilic. It grabbed water out of the atmosphere and it could dissolve itself. We also talked about salt in New Orleans, right? Things that in high humidity locations, you have to put rice in salt shakers because things that grab water out are deliquescent and they dissolve themselves. Well, in the human body, large biological molecules such as proteins are kept in suspension by surrounding water molecules. The macromolecules fold up so that hydrophobic groups are away from the water and hydrophilic groups interact. Let me show you the example. Okay, here's a big molecule. So once again, hydrophilic guys are going to grab the water because they have charges. Remember we said water is an extreme dipole and it grabs onto the charged ends of this molecule. But then The inner part of it here might be very nonpolar, and therefore it's hydrophobic. Who cares? What does this mean? Well, there's some good examples of it. And soap is one of these examples. And this is why soap works so well. Because soap is both hydrophobic and hydrophilic. It's got a polar end. So remember we talked about doing your wash. If you want to clean your wash, you want something that has a polar or a charged end so it can dissolve all those inorganics or all those molecules that are polar or ionic. So the dirts would be washed out with one end, the hydrophilic end, or the charged end, and then this long chain of organics in a soap would actually dissolve the non-polar molecules, like the grass stains or the ballpoint pen that we talked about in class. So here's another example of soap molecules. Once again, there's the oil droplet. So we have this long fatty part of our soap that dissolves the non-polar molecules, and then that big charged head on it, that this happens to be a sulfate group, obviously, right? But you see it has a charge. So the charge is going to grab onto the water. Here's another example. This is an animation that's going to start in a minute. But we can take a triglyceride, a fatty molecule. Have you ever made soap? Well, you take fat, pure lard, and the lard itself you mix with sodium hydroxide, which is lye. And the lye, like we used in class the other day, this really strong base, when you mix it with lard, fat, we actually get soap. Here it goes again. We have a triglyceride, which means 3 fatty acids connected to a glycerol. But when we add the sodium hydroxide, the glycerin group breaks off, and we get a charged sodium group on the end of each soap, and a big fatty molecule, the fatty acid. Once again, hydrophilic, hydrophobic. But that's why soap works. We've got both of those ends to start to dissolve things. What about in your own body? Look at your own body. Your gallbladder excretes bile. But a bile salt forms what we call an emulsion. It's got one end that's charged and one end that's not. And it emulsifies some of the chemicals in our body to help us digest. Here's another example of an emulsifier, because these molecules, just like soap, have 2 ends, one's polar and one's nonpolar. We know in the middle here, oil and vinegar don't mix, right? This is typically what you see on the left-hand side when you make an oil and vinegar salad dressing. But have you ever seen some oil and vinegar salad dressings that actually do mix? It is possible. What do? Well, we take a soy product called lecithin, look like little soybeans, we grind them up and look at your lecithin molecule. It's got a charged end and, just like soap, a non-charged end. We're not eating soap, by the way. It's a soy product. But when we add it to salad dressing, the polar end is going to grab on to the vinegar side, and the non-polar end is going to grab onto the oil. And so you get, ta-da, voila, there's our oil and vinegar dressing. Now it's creamy. That means it doesn't separate because of this emulsifying agent. So an emulsifying agent is like soap, something that grabs both polar and non-polar molecules, so things don't actually break apart. And we can get things to actually sort of form into what's not really a solution, but it looks like a solution to us. They won't separate. They will stay blended much longer. So there's our salad dressing with our emulsifying agent. Let me just go back for a minute before you start the walk around, because I did skip, I will find it here. We did molarity, but we did not do here we go, molality. So we talked about molarity, moles over liters, but on your worksheet tonight for homework, I also want you to do molality. So how is molality different? Calculate the molality of a solution made by adding 4.5 grams of sodium chloride to 100 grams of water. So you're going to find moles. You can do that, right? Periodic table. But now this time, instead of moles over liters of solution, we're going to dissolve it in a kilogram of water. So here we're just showing grams divided by 1,000 gives us kilograms. So if you're given grams, convert it to kilograms, but not solution. So molality is moles divided by how much water, and the water's in kilograms. Little bit different twist on molarity. Moles divided by kilograms is solution. We use molality because its value does not change with temperature. I don't know how often you'll use it, but here you have it, molarity and molality. Molality over kilograms of solvent. Now, you've got, I don't think there's 22 questions. I think it's only 15 questions on the molarity walk around, and they're in the center cart, and then everything else is around the sides of the lab bench. And go ahead and finish the walk around, turn it in, stamp it, turn it in, and that's it. All right, see you on Friday. Good luck. Bye.